So we're going to be continuing our talks on transient analysis, but we are going to be supplementing things. Simmer down. So the first thing that I want to talk about is the concept of a time constant. Okay. So a time constant is to an electrical engineer what a half-life is to a chemist. It is just a means by which to quantify the rate of decay of exponential signals. But because we're electrical engineers, we do it differently for whatever reason. Can't tell you what that reason is, but we do it differently, okay? So if we have a signal, let's just say for the sake of argument that it is a voltage signal that exponentially decays from some initial value, which I'm going to call it V naught, like so. Its rate of decay, or the mathematical expression for this signal, would be V of t is equal to that voltage V naught, e to the minus t divided by tau volts, where tau is our time constant for our system. Mathematically, what tau is, and I know this is going to seem real weird, but tau is how long it takes for this signal to decay to 0.368 of its original value. Okay, so it decays to roughly 37% of its original value. Okay, and so tau in this case is what happens when, if we have negative t over tau, at exactly tau, we have V naught times e to the minus 1. Okay, so that's where that 36% gibberish comes from. So at 2 tau, our value would be V naught times e to the minus 2. And at 3 tau, it will be V naught times e to the minus 3, etc. So I'm going to make a simple table here. Tau and percent. So actually, right. So 1 tau is e to the minus 1, is 36.79%. 2 tau is e to the minus 2, which is 13.53%. 3 tau is e to the minus 3. Oh goodness, what the heck just happened? Which is 4.98%. 4 tau is e to the minus 4, is 1.83%. And 5 tau, e to the minus 5, is 0.67%. Okay. So in 5 time constants, our signal decays to less than 1% of what its initial value was. For electrical engineers, 5 tau represents infinity. Okay, That's how long approximately it takes our capacitor to fully discharge or fully transfer its energy to a resistor, and the exact same thing for an inductor, okay? So, yes, sir.
Are we going to need to remember the percent?
Not, you can e to the -1, e to the -2, e to the -3, et cetera, in your calculator. You don't need to remember anything. Just remember that time constants are related to e to the minus something, and you're good to go, okay? Yeah, remembering those percents is completely useless. I didn't do it. I used my calculator, all right? So this time constant represents how long it takes for a signal to decay to a specific point, all related to the e to the minus power thing. So if we have an RL circuit, what do you think our time constant is? L over R, exactly right. Right? Because we know that for RL circuits, we have some initial value e to the minus R over L times T, which means tau should be the inverse of that thing that's being multiplied by T, right? Similarly, for RC circuits, we will have tau is equal to what? 1 over RC, okay? So you may be asking yourself, well, why am I harping on this stuff? The circuits that we are about to deal with are going to be what are called total response problems, okay? And I am going to create a generic way to solve any of these total response problems, very similar to what we did for RL circuits, source-free RL circuits on Wednesday, as well as source-free RC circuits. But I'm going to modify, I believe it was step 4, which said calculate LEQ or calculate CEQ or whatever, to just be determine the time constant so that it's the exact same step regardless of any circuit that we have, okay? So if you can remember these two simple relationships, and that the voltage drop across a capacitor does not change abruptly, and the current flowing through an inductor does not change abruptly, you effectively have all of the information you will ever need to know with regards to how to analyze practically any and every first order transient analysis problem you could ever see. All right. So let's talk about total response now. So the total response of a circuit is a combination of what's called the forced response and the natural response. So we could say in general that YT, which is our total response as a function of time, is equal to the natural response plus the forced response. This natural response is exactly what we were solving for on Wednesday, okay? It is how the circuit behaves when there are no sources left in it. So only thing that we have is some equivalent inductance connected to some equivalent resistance, or an equivalent capacitance connected to some equivalent resistance. Our forced response, we haven't really figured out yet, but it's going to be pretty dang easy to figure out, okay? So if I have the following circuit, let's say that it's a capacitor related circuit this time, where I have some voltage Vs of t connected to a switch, and now our switch is closing instead of opening. Here's our resistor R. Here is our capacitor C. And here is our quantity of interest, VC, as a function of time. What our forced response represents is the value of this quantity of interest at t is equal to infinity. So what I mean by that is it is the value of that voltage when it is being forced or excited by that voltage source. So if we look at this circuit and we analyze it from a transient perspective, right? At t is equal to 0 minus, the voltage source is not connected to the resistor and it is not connected to the capacitor. So we should expect to see that there is no voltage drop over the capacitor and there are no currents or anything flowing around the right-hand side of the circuit, right? It's disconnected, so why would there be? Once that switch closes, there's now going to be an energy transfer, right? So effectively what's going to happen is that capacitor is going to start charging, right? And after a long period of time, or roughly 5 time constants, that capacitor will be fully charged, and then it will stay at that fully charged level. That is the forced response. That voltage source is forcing the capacitor voltage to be Vs after a long period of time. Everybody okay with that? That's all the forced response is. It's just a DC value for the voltage at t is equal to infinity, or a long time after the transient condition has occurred. Okay. So I'm going to write that down. Sorry, that is not correct. YF of t equals to infinity. Okay. So we know what the natural response, how it behaves. We know how the forced response behaves now. So let's solidify these things by working a numerical problem. And we're going to find that there's going to be one small change that we need to make in order to develop kind of a unified way of approaching all of these problems. Okay. So let's look at this exact guy. So let's put numbers on it. Let's say that we have a 10-volt source. We have a switch that closes at t is equal to 0, connected to a 5 ohm resistor, and let's call this a 100 millifarad capacitor. And let's say that we are interested in this capacitor voltage VC as a function of time. And just for the heck of it, let's look at this resistor current as a function of time too. So even though the switch is going in the opposite direction from what we had the other day, meaning that Wednesday we were taking sources out of the circuit or out from influencing the behavior of our energy storage elements. Today we're seeing what happens when we switch sources in to influencing the behavior of our elements, all right? So our first step would be to analyze the circuit. At E is equal to 0 minus. So for our circuit, this should be pretty dang trivial. Since before the switch opened, we are at DC steady state. I'm replacing my capacitor with an open circuit. And I am trying to figure out what this quantity DC at 0 minus is, as well as this quantity IR at 0 minus. Anybody have any thoughts on what these should be? We talked about it like 4 minutes ago. 0. They're disconnected, so it seems pretty reasonable to assume that the current flowing through the resistor is 0 and the voltage drop across the capacitor is 0. Next, we would analyze our circuit. Sure. Exactly right. All open circuits, no current can flow anywhere. If there's no current flowing through that 5 ohm resistor, then there obviously isn't a voltage drop over the 5 ohm resistor. And since the 5 ohm resistor is in parallel with the capacitor, that means there's no voltage drop over the capacitor either. Number of different ways that you can think about what's happening here, but it all results in the same thing. If the voltage source isn't connected to the network, there shouldn't be any energy stored in it. All right, step 2 is to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch has closed. So here we have our 10 ohm resistor. Excuse me, a 10 volt source. What the heck am I thinking? 5 ohm resistor. Yeah, I made a mistake. It happens a bit. So let's talk about what's going to happen with our capacitor here, because I don't think we talked about this much on Wednesday. We know that the voltage drop across the capacitor cannot change abruptly, right? So our voltage drop at t is equal to 0 plus has to be what? 0 volts. Sorry. VC at 0 plus has to be 0 volts. Okay. So when we dealt with our inductor problems, I said that at the exact instant in time, t is equal to 0 plus, our inductor behaved as if it were an independent current source because there was a fixed amount of current flowing through it, and any voltage that it needed to peer across its terminals could. For a capacitor, they will behave like an independent voltage source because the amount of voltage across them is fixed at this instant of time, regardless of how much current is passing through it. Now, this is an interesting problem here. How do we represent a 0 volt voltage source? A short circuit, okay? So because the voltage drop across the capacitor was 0 at t is equal to 0 minus, that is why we are going to model it as a short circuit at t is equal to 0 plus. So this isn't a, you can do it as a short circuit every time by any stretch or you can't do it all the time is what I'm trying to say. You can only do it when V at 0 minus was equal to 0 volts. If it had happened to be 3 volts, we would model it as a 3 volt source. If it happened to be 15 volts, we would model it as a 15 volt source. Because VC at 0 minus was 0 volts, we are going to treat this as if it were a short circuit. So what must IR at 0 plus be?
If the traffic becomes a short circuit, wouldn't we then be able to measure a 10 voltage drop across it?
All right, so I see I've introduced a little bit of a problem here. So the problem that I have introduced here is that there's no resistance, so I have a 10 volt drop equaling a 0 volt drop at the same time. So I'm going to go back to my previous circuit diagram and fix this ever so slightly. Okay. That is exactly right. Right. So if I include some resistance here, let's call it a 5 ohm resistor. and I apologize for not thinking about this earlier. If I connect a practical voltage source, does anything change with what I saw at t is equal to 0 minus? Not at all, right? Now, I no longer break the laws of physics by making 10 volts equal to 0 volts. Again, I sincerely apologize for that oversight on my part. We now have a circuit we can actually analyze, and I hope that the confused looks go away. Sure. So I had 10 volts in parallel with a 5 ohm resistor. Everything is A-OK. In parallel with a short circuit. By definition, the voltage drop over a short circuit is 0 volts. So I can't have 0 volts across my 5 ohm resistor and 10 volts across my 5 ohm resistor simultaneously. Does that make sense? So because they're all in parallel, I was forcing 10 volts to be, the voltage drop across my short circuit to be 10 volts, and it can't be that. Yeah. That's exactly why it's an ideal voltage source. So it can't be connected to 0 resistance because that is forcing a voltage and no voltage to occur simultaneously. Can't happen. Two can't be 1, right? So by using the practical source here, we fixed that mistake on my part. You would have never noticed this if I weren't a jackass and remembered it in the beginning. Okay, so circling back around, what is the current flowing through my resistor, IR at 0 plus? What was that? 0. Why? Yeah, that's exactly right. There's obviously going to be some current that's leaving my voltage source now, but none of it is going to flow through that 5 ohm resistor, which I've defined the current IR over, right? All of it is going to bypass it. So a question that you might be asking yourself here, and that would be a perfectly reasonable question, is if the system didn't, if the system had these particular values of 0 volts and 0 amps at t is equal to 0 minus, and then it had those same values of t is equal to 0 volts and 0 amps at t is equal to 0 plus, do we actually have a transient condition because nothing has changed? We do, because over time, our forcing function, our DC source, is going to cause the voltage across our capacitor to increase, okay? So even though we don't see a change from 0 plus, or excuse me, from 0 minus to 0 plus, we still have a transient condition because changes are occurring.
Isn't that the fact that IR is 0, is that just because all the current is now routed into the capacitor?
Exactly right.
That's becoming this voltage.
Yep. So step 3 will be to analyze the circuit at t is equal to infinity. Now, when we did this step on Wednesday, the answer was inherently 0 because we had disconnected our sources so that all of the energy stored by our capacitors and inductors was transferred to the resistor, and after a very, very long time, all of that stored energy became heat. We're describing a charge cycle now, right? So we should expect that it starts from no energy stored and works towards having some finite amount of energy stored. So at t is equal to 0, or excuse me, that t is equal to infinity, our circuit is going to look like this, right? We have our 10 volt source. We have our, let's fix Dr. Hartman's mistake, 5 ohm resistor. We have our other 5 ohm resistor. And now I have a question for you guys. What do you think I should model the capacitor at here? Okay, so let's think about this. T is equal to infinity is a long time in the distant future, okay? It represents time after the transient condition has occurred. So it is, t is equal to infinity, represents another DC steady state condition, right? So we have a DC steady state condition for t less than 0. We have a DC steady state condition for t greater than infinity. And in the middle there is where our transient condition is occurring.
Charging the capacitor or decay?
So at this point, it's representative of when the capacitor is fully charged. So the capacitor is seeing a DC circuit because the voltage drop across the capacitor is no longer changing.
So would it be an open circuit because that's current close to a full charge capacitor?
Exactly correct, okay? So because the capacitor is fully charged at t is equal to infinity, we treat it as its DC steady state equivalent, which is an open circuit. So we'll have VC at infinity here. We'll have IR at infinity here. So who can tell me what either of these quantities should be? So you're saying that IR, the current flowing through the resistor, should be 0? Nope. I'm looking for the current flowing down through that 5 ohm resistor in the middle branch. Drew. Okay. So 10 volts divided by 5 ohms plus 5 ohms is equal to 1 amp. I agree wholeheartedly, right? So all the current that leaves the positive polarity terminal of the voltage source has to flow through that top 5 ohm resistor, and then none of it can branch off and flow down, or excuse me, flow to the right through the short circuit or open circuit, gosh. So all of it must flow down through that middle 5 ohm resistor. So we have 10 volts over 10 ohms is equal to 1 amp. So if the current flowing through that middle branch 5 ohm resistor is 1 amp, what's the voltage drop across the capacitor? 5 volts, because the capacitor is connected in parallel to that resistor, right? So we have to have 5 volts here, or we could have just done voltage division. Either way works, right? So because it's the voltage drop only over the second 5 ohm resistor, not both of the 5 ohm resistors, right? So the capacitor voltage is measured between this point in the circuit and this point in the circuit. 10 volts occurs between here and here, right? So if we have two 5 ohm resistors connected in series to a 10 volt source, what's the voltage drop over either of the 5 ohm resistors? 5 volts. All right. Step 4 will be to determine the time constant for the system. And I'm going to put here, it should be redundant actually, during transient. Condition. So we're going to calculate our time constant in the exact same way that we determined things on Wednesday, okay? For this particular problem, there's only one capacitor, so I feel pretty strongly that we can all agree that the equivalent capacitance is C is equal to 100 millifarads. Am I okay with that? No, hopefully no room for argument there. All right, to determine my equivalent resistance seen by my capacitor, it's the Thevenin resistance seen by my capacitor, which means I need to be looking at the dead network. So my voltage source will be short-circuited. It's during the transient condition, which means my switch is closed. So I'll have the 5 ohm resistor connected to this other 5 ohm resistor. Here's where my capacitor is. But since I'm finding the Thevenin equivalent with respect to this capacitor, what do I have to do? Take the capacitor out and look in through the terminals where the capacitor was. So what do I see? 2.5 ohms, 5 ohms in parallel with 5 ohms. So from this, I think we might have made a mistake earlier, but it'll be okay. So my time constant here, okay? Let me talk about where I think we made a mistake and I just went with it. Yeah. The time constant for an RC circuit shouldn't be 1 over RC, right? It should just be RC because we have e to the negative t over tau. So for our RC circuits, it was already t over RC. So that's why it should just be RC by itself. So I apologize for not catching that earlier. I'm making all kinds of mistakes today. Very, very sorry. That is a fantastic excuse. I'll bandwagon that all day. It's Friday. So we have 2.5 ohms times 100 millifarads should be 0.25 seconds. And for reasons you will see shortly, the inverse of tau would then be 4 per second. So step 5 is going to be apply our generic equation here, but we need to add something to it because we have a forced response, all right? So I'm going to ask you guys to not write down this equation because you're just going to have to erase a portion of it a moment when we have to make a correction. And I want to explain where that comes from. I figure you'll be frustrated if you write it down and then I literally make you erase it 20 seconds later. So I'm just giving you fair warning. So we know that our natural response, yn of t, should be of the form y at 0 minus for t less than 0 minus, and y at 0 plus e to the minus t over tau for t greater than or equal to 0 plus. And we know that yf of t is just y at infinity. So it seems like our total response should then be this: y at 0 minus for t less than 0 minus, and y at 0 plus e to the minus t over tau plus y at infinity for t greater than 0 plus. So I've simply just added on my forced response, and I added on specifically to what's happening after t is equal to 0, because infinity occurs after t is equal to 0. Okay. So if we use this formula to determine our capacitor voltage, we'll actually run into a small problem here. All right. So what was y at 0 minus? 0 volts. What was y at 0 plus? So we'll have 0 e to the minus 4t plus what happened at y is equal to infinity? 5 volts. T greater than or equal to 0 plus. Anybody see the problem here? Exactly right. Our capacitor voltage jumps instantaneously from 0 volts to 5 volts and stays there in perpetuity. We know that that can't happen, okay? So the change that we need to make for our generic formula is actually very straightforward, all right? I'm going to erase this part right here. And I'm going to say that this should be y at 0 plus minus y at infinity, e to the minus t over tau plus y at infinity, t greater than or equal to 0 plus now. So when I make that change, what happens to that coefficient in front of my exponential? Well, I have 0 minus 5 volts. So it's just going to be minus 5. And so now we can see that if we plotted this thing as a function of time, this is 5 volts. What our capacitor voltage will do is it'll go away thing, start at 0 and begin to exponentially increase. Or it's actually, this is going to look like one minus e to the minus t over tau. So this is telling us how it's charging, okay? That change right here is actually required for all signals, okay? So this is our generic formula now. We're determining the response for any and every voltage and current signal in a first order transient analysis problem. Doesn't matter if it's an RC circuit, doesn't matter if it's an RL circuit. Technically, it doesn't even matter if it's a total response problem or a natural response problem, because for the natural response problems, y at infinity was 0. So this generic formula literally works for any and every linear first order circuit. All right. Anybody have any questions before we work another example problem, reinforcing these concepts? All right. Do I need to go back? I'm sorry. No. This differs from yesterday because now everything isn't 0 at t is equal to infinity. Things will have finite values at infinity, and that could not happen on Wednesday because we were taking sources out. Now we're putting sources in, so we're forcing quantities to have DC values after a lot of time has elapsed. Okay, it's a small distinction, but it's a very, very important distinction. All right. Okay, so let's say that I have the following circuit. Oops, let me change to black here. And I am telling you very explicitly the problem that we were about to work, and I promise you guys that you actually have the circuits knowledge to do it. is going to be harder than anything I would ever put on your exam. Yep, it keeps going. I'm doing a problem of this level of difficulty because if this makes sense to you, you're in fantastic shape for our upcoming exam, which occurs 1 week from Monday. All right. So this is our humdinger of a circuit. We are going to use those 5 steps, just like we've done everything else. The first 3 steps are going to involve figuring out what our different parameters are at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity, respectively. Step 4 will be determining the time constant for this circuit, which that one will be a little bit difficult because we have a dependent source, but that's really the only thing that makes it difficult. And then step 5 will be plugging in our information to our generic circuit. Okay. So let me ask you guys, and I think this is actually kind of interesting question. Do you understand why this is a transient analysis problem? So let me talk to you about what I mean by that question. In every circuit that we analyzed on Wednesday, the switch wound up taking a source out. And our rudimentary example that we worked a few minutes ago involved adding a source in. What does this switch do? Yeah, it just puts the resistor in or out. But it's still causing a change in the circuit, which means this is a transient analysis problem. Transient analysis is all about things changing from a DC steady state condition over time to another DC steady state condition. So moving a resistor into or out of a circuit by short circuiting it or opening circuiting it here is absolutely cause for a transient condition, even though it has nothing to do with moving a source into or out of the circuit. Okay. All right, so step 1, let's analyze at t is equal to 0 minus. So at t is equal to 0 minus, our circuit is going to look like this, right? We have our 12-volt source here. We have a 6 kilo ohm resistor here. Our switch is closed, which means that second 6 kilo ohm resistor is short circuited, so I'm not going to draw it. I have my 4 kilo ohm resistor here. Six kilo ohm resistor, dependent current source. Three kilo ohm resistor. Because we're at DC steady state, my capacitor looks like an open circuit. Here's my voltage VC at 0 minus. Here's my current IR at 0 minus. here is my current IA at 0 minus, and we're going to have to figure out all three of those quantities. So how would you guys like to approach this? So I hear mesh, and I'm okay with that. The reason I personally wouldn't do mesh would be because that's going to make it not necessarily difficult to determine that quantity VC at 0 minus, but a little bit harder than it would be by using nodal analysis. That being said, since so many of you prefer mesh analysis to nodal analysis, I'm going to work it with mesh, and I'm going to talk you through figuring out what that voltage is. Okay. So if we're going to use mesh analysis for this particular problem, I'm going to label this as my mesh current, and I'm going to call it I1, and I'm going to call this guy I2, and I am not going to put a mesh current in that third bit there because there's an open circuit, so no current is flowing through it. So there's not a mesh current. Okay, so if you have a question about that, that's why I'm not doing it. All right, so I have a dependent source. So I need to, first off, to express my dependent quantity, which is IA, in terms of my mesh current. So what's my equation for IA in terms of my mesh currents? So IA is this guy in the top left-hand corner flowing through the 6 kilo ohm resistor, right? Might be hard to see my writing from that far away. I1, or I1, exactly equal to I1. All right. I have a current source in my circuit. So I'm going to need my current relationship. Okay. So I know that twice IA at 0 minus is equal to what? Negative I2. So I can substitute, I can make a substitution here because I think that's what you're referring to. Okay, so you're saying, all right, I see what you're saying. Okay, well, it's going to be the exact same result as if I do the substitution. So I'm just going to do the substitution. So twice I1 is equal to negative I2, which would give us 2I1 plus I2 is equal to 0. So that's one of the two equations that we need. Where's our second equation going to come from? Exactly right. Kirchhoff's voltage law loop around mesh 1. So, Tyler, I'm going to pick on you. How do I do mesh here? I'm starting from the bottom left-hand corner, and I'm following I1 around its clockwise path. Negative 12 volts, thank you. What's next? Six kilo ohms times my mesh current I1. All right, what's next? So you're close, but there's a small mistake, right? Since that 4 kilo ohm resistor is between two meshes, it should have two mesh currents pass through it, right? So that mesh current I1 is going to flow down, so it's going to get the positive sign. That mesh current I2 is flowing up, so it's going to get the negative sign. So we're following I1 around its path. So since I2 is in the opposite direction, it gets that negative sign. Thank you. So here's equation 2. And we can solve these guys, right? So let's take just a moment to do that. $10,000 I1 minus 4,000 I2 is equal to 12. So I get, sorry, 2/3 of a milliamp and 4/3 of a milliamp. Anybody else? Can anybody else verify that? All right. Oh, yeah, you're right. Absolutely right. I'm sorry for that. Negative 4/3 of a milliamp. Thank you. Okay, so now that we know what mesh current I1 is and mesh current I2 is, we obviously know that IA at 0 minus is 2/3 of a milliamp. And we know that IR at 0 minus is going to be what? Right, so 2/3 minus negative 4/3 is going to look like 6/3 or 2 milliamps. I believe. And now we come to VC. Anybody have any thoughts on how we might determine VC? Across what resistor? The 4K resistor? I disagree.
The 6K on the right plus the 4K. Also 0.3 going on, but that will stop the trip.
I'm not entirely sure.
Yeah. So the voltage drop across the right node is 4. What's the voltage drop across the 4?
Okay, I see what you're saying. I'm going to do it slightly, in my opinion, easier. I understand exactly what you're saying. I am going to choose do my Kirchhoff's voltage law loop around the outside, because then I just have things. So I know that that 6 kilo ohm resistor on the left is just multiplied by I1. That second 6 kilo ohm resistor is multiplied by I2. There's no opportunity for me to make any silly mistakes about forgetting parts. It's just a simple KVL loop, right? So I could say that negative 12 volts plus 6 kilo ohms times I1 plus 6 kilo ohms times I2 plus VC at 0 minus is equal to 0, which means VC at 0 minus is simply 12 volts, dang it, minus 6 kilo ohms times 2/3 of a milliamp plus 6 kilo ohms times 4/3 of a milliamp. I've got my signs right, and I believe I do. Excuse me. So 12 minus 6x. I get 16 volts. Everybody okay with that? Kirchhoff's current, or excuse me, Kirchhoff's voltage law around that outside loop. And the reason why this plus sign right here exists is because I know that I2 is negative. Okay. All right. How do you guys feel about our analysis at t is equal to 0 minus? Definitely a bit lengthier than any of the previous problems that we have worked, but was there anything new or tricky? Other than thinking about how to figure out that particular voltage using mesh analysis. Other than that, it was fairly straightforward. All right. Yes. So let me explain why I believe that nodal analysis would have been easier without solving for anything. Okay. So if I had done nodal analysis here, and I'm going to do what I would have done in blue, I would have chosen this guy as my ground. I have a voltage VA here. And let's call it V1 just so that I'm not using alpha numeric or alpha subscripts. V1 and V2 here. If I can solve for those two quantities, IA is just 12 minus VA over 6 kilo ohms. IR is just V1 over 4 kilo ohms. And VC at 0 minus is just V2. So that's why I believe nodal analysis would have been a better method by which to solve this particular circuit. Because the currents would be easily defined in terms of the mesh, or excuse me, in terms of the nodal voltages. And that voltage VC is given to us instead of having to work for it. But we can absolutely do it using mesh, because we just showed how. So. Let's now analyze our circuit at t is equal to 0 plus. So now our switch from our original circuit has opened up, which is going to put another 6 kilo ohm resistor into the circuit. So it should look like this. Here's our 12 volt source. We see 6 kilo ohms in series with 6 kilo ohms. Here is our 4 kilo ohm resistor. Here is our third 6 kilo ohm resistor. Here's our dependent source. Here is our 3 kilo ohm resistor. And so I ask you, what should I be modeling my capacitor as now? A 16 volt source, right? So my capacitor is going to be replaced by a voltage source that has the same value and same polarity as VC at 0 minus. So that's why we'll have a 16 volt source right here. And let me just define my other quantities of interest. IR at 0 plus, IA at 0 plus, and this guy is twice IA at 0 plus. So I want to find IA at 0 plus, IR at 0 plus, and we know that VC at 0 plus is 16 volts. So we don't have to work for that guy at all. So we are replacing our capacitor with a 16 volt source because the voltage drop across our capacitor at t is equal to 0 minus was 16 volts, okay? So at the exact instant in time, t is equal to 0 plus, since our capacitor voltage cannot change abruptly, whatever it was at t is equal to 0 minus, it must continue to be at t is equal to 0 plus. So that's why it's 16 volts, and it needs to have the exact same polarity as VC was defined to have. All right, those are the two. How could I go about solving this circuit for these two currents of interest, Alexis?
I would combine the two resistors series and then do the out.
Okay, so for this one, nodal and mesh are probably about the same, although actually now that I think about it, nodal will be a little bit easier because you only have two unknown quantities. So what Alexis is suggesting is that we can combine these two 6 kilo ohm resistors into a single 12 kilo ohm resistor, which eliminates a node. And then she has suggested that we do nodal analysis. So I'm going to call this voltage V1 and this voltage V2. And knowing these two nodal voltages, I should be able to determine my currents IA and IR fairly easily. And I agree. So, yes, Tyler. We do, but it's 12 volts, right? If we choose the bottom as our ground, we actually have two super meshes because we have two voltage sources. But because ground is our bottom node, those super meshes are between that node and ground, which means that top left nodal voltage is exactly 12 volts. That top right nodal voltage is exactly 16 volts. They're not unknown, so I didn't include them. But that's a reasonable question. All right. So I'm going to apply Kirchhoff's current law at node 1. So I'm going to ask for you guys' help. To be clear, I want the current directed to the left, the current directed down, and the current directed to the right. So who can tell me what the current directed to the left is? Benjamin. Absolutely correct. Somebody else tell me what the current flowing down through the 4 kilo ohm resistor is. Pardon? V1 over 4 kilo ohms, exactly right. What about the current flowing to the right through the 6 kilo ohm resistor? V1 minus V2 over 6 kilo ohms, absolutely correct. Set these guys equal to 0. Next, we would do, I'll try to squeeze it in here, KCL at node 2. And let's do these in red. So this will be this current directed to the left, this current direction down, this current directed to the right. So who can tell me what the current to the left is? Exactly right. What about the current directed down? Minus 2IA, okay. So I made a small mistake here, so let's rectify that right now. I forgot to express my dependency current IA in terms of my nodal voltages at the beginning. Let's do that. So IA would be what? Exactly right. 12 volts minus V1 over 12 kilo ohms. And so I'm going to go ahead and substitute that in right here. If the if the negative polarity terminal were on top and the positive polarity terminal were on bottom, it would be negative 12 volts minus V1. You're absolutely correct. All right, what about the current flowing to the right through the 3 kilo ohm resistor? V2 minus 16 volts over 3 kilo ohms is equal to 0. Okay. So let's solve these two guys and figure out what V1 is and what V2 is. So you would move 12 volts divided by 12 kilo ohms to the other side. Yes. So I wouldn't call that +1. I'd call that +1 times 10 to the -3 or a milli. Let's see here, 1 over 6,000 plus 1 over 3,000. And then I'm going to have 2 times 12, 12,000, so 24 over 1,000 plus 16 over 3,000. All right, who got values? Are you raising your hand, Elijah, or are you scratching your elbow? Okay, scratching your elbow. That's all right. Anybody get anything? That's what I got. I know I'm a smart fella, and I think you're a smart fella, so I'm going to say you're correct. What'd you get for V2? 44 over 3. All right. So, assuming that those answers are correct, by all means, continue to take another minute or so to verify them. How would we go about determining that current IA and that current IR? It has been written down on the screen. Yeah. We use that equation, so 12 volts minus V1 over 12 kilo ohms. Right, so that would be 12 minus X over 12,000, which is 0.4 26 milliamps. Sorry, that should not be a B, that should be an R. My apologies. What should IR be? Exactly right, just V1 over 4 kilo ohms. which comes out to be 1.722 milliamps. All right, so other than the headache of entering this jazz in the calculator, did any portion of our analysis at t is equal to 0 plus not make sense? Anybody have any questions about the analysis that we did? Anybody want me to explain anything further or try to explain it in a different way? All right. Are we good to move on to our analysis at t is equal to infinity? All right. So at t is equal to infinity, our circuit is going to look like this. We have our 12-volt source. We have our 6 kilo ohm resistor. Another 6 kilo ohm resistor. Our 4 kilo ohm resistor. Another 6 kilo ohm resistor. Our dependent current source. Our 3 kilo ohm resistor. And just to try to reinforce things here, what should my capacitor be represented by at t is equal to infinity? An open circuit, because t is equal to infinity represents the beginning of another DC steady state condition. So here is VC at infinity. Here is IR at infinity. Here is IA at infinity. Brandon. No, it's an open circuit. That's a good question. So we don't know what that voltage is at t is equal to infinity. If we knew it was 0, we would have just replaced it with a short circuit, right? We're trying to figure out what it is, and we are doing that by assuming that a very long time after the transient condition has occurred, our system has reached DC steady state again. So we're looking at this circuit at a time after things have stopped changing, which means we get to treat our capacitor as if it were an open circuit. If we had an inductor here, a very long time after things stop changing, it would look like a short circuit, right? So we just use our DC equivalent. Good question though. All right, how would we analyze this guy? Any thoughts? Okay, so put these two 6 kilo ohms together as a 12 kilo ohm. I'm on board with that. What next, Sarah? Nodal. I think nodal would be easier. So let's call this guy V1 and this guy V2. Okay, so this is going to go back to Tyler's question slightly a couple of minutes ago. So I want to explain this. I know that I've talked about it before, but I want to be very, very clear about what's going on here. I could call this node out here on the right, node 3, right? Because it is technically another node that I am not accounting for. But because I recognize that no current is flowing through the 3 kilo ohm resistor because it's not part of a closed current carrying loop, V2 as it is drawn and V3 represent the exact same voltage. So that's why I am choosing to ignore this node over here, because I know that the voltage drop VC will be the exact same thing as my nodal voltage V2. Adding that extra variable just complicates things. Does that make sense? They're not. No current flows through the 3 kilo ohm resistor, which means there is no voltage drop over the 3 kilo ohm resistor, which means the 3 kilo ohm resistor is behaving as if it were a short circuit. Right? No current can flow through it because it's not part of a closed current carrying loop. Exactly right. The voltage drop over it will be 0 because Ohm's law tells us that V is equal to I times R. And if I is 0, V has to be 0. So VC, and I'll write this down just so we don't forget about it in a moment, at infinity is the exact same thing as that nodal voltage V2. All right, so I'm going to have this current directed down, or excuse me, to the left, this current directed down, this current directed to the right when I do KCL at node 1. So somebody tell me what this should look like. I'll give you a big hint. It's exactly what it looked like when we did nodal analysis on this circuit a minute ago. Literally nothing has changed with regards to how things are connected to node 1. Right? So we'd have V1 minus 12 volts over 12 kilo ohms plus V1 over 4 kilo ohms plus V1 minus V2 over 6 kilo ohms is equal to 0. When we do nodal analysis or KCL at node 2, I'm intentionally not drawing my current to the right because I know it's 0. So it's fruitless to even put it in my equation. So what should I have? Alan, you got any thoughts? Sure, you're absolutely correct. I forgot it again. IA at infinity. Does it change at all from what we had a moment ago? Not at all, right? So it's just going to be 12 volts minus V1 over 12 kilo ohms. Thank you for pointing that out. So what should my current flowing to the left through that 6 kilo ohm resistor be? Yeah, so it's effectively going to be the exact same thing as we had last time, except that the V2 minus 16 over 3 kilo ohm bit is now 0, right? A perfectly reasonable approach. So V2 minus V1 over 6 kilo ohms minus twice IA, where IA is 12 volts minus V1 over 12 kilo ohms is equal to 0. And now we solve for V1. Anybody get a result? Pardon? I got 4 and 12, but I might have typed something in wrong. All right, let's say it's 6 and 12. 6 volts and 12 volts. So that means VC at infinity is 12 volts. What is IA going to be? 12 minus 6 over 12 kilo ohms, so or half a milliamp. My mental math is correct. And IR at infinity should be V1, which is 6 volts divided by 4 kilo ohms. So 6 over 4 looks like 3 halves of a milliamp. That is correct. Anybody have any questions regarding our analysis here at t is equal to infinity? All right, so the next thing that we need to do is to determine our time constant. All right. So just to repeat, I know I'm sounding like a broken record. We are doing this during the transient condition. So that means after the switch is opened up and when that middle 6 kilo ohm resistor is in play, right? So during the transient condition, my system looks like this. I have my 12 volt source, 6 kilo ohm resistor, 6 kilo ohm resistor, 4 kilo ohm resistor, 6 kilo ohm resistor, sorry, there should be a 3 kilo ohm resistor there. And here's my capacitor. Here is where IA is. And since we know that our equivalent capacitance C is going to be the only capacitor value we have, so I'm gonna have to scroll up for a minute because I've forgotten what that is by now. 100 micro, thank you. I think it's micro. So my intention is for it to be microfarads. Okay, so perhaps my mu looks like an M, which I can definitely look at it and see why that would be confusing to somebody. So we're going to treat it as if it's microfarads. All right. So I would take my capacitor out, and I'm trying to find the Thevenin resistance looking in. Now I have a little bit of a conundrum here, in as much as I have a dependent source. So it's no longer going to be simple resistor combination techniques. Brandon. So that is a fantastic question. And the short answer is, it depends on how we go about determining that Thevenin equivalent resistance, okay? So let me explain what I mean by that. If we were going to use the test source method to determine that equivalent resistance, we would absolutely need to apply our test source to a dead network. You're 100% correct there. But there is another method for us to determine the Thevenin equivalent resistance of a network containing a dependent source. It's simply the ratio of V Thevenin, the open circuit voltage for this circuit, divided by I Norton, the short circuit current for this network. Now, if we scroll up here and we analyze this circuit at t is equal to infinity, What does VC represent? The open circuit voltage. So we already know what VThevenin is. So the question then begs, is it easier to calculate I Norton, or is it easier to apply the test source method? So what do you guys think will be easier to do? Apply the test source method to this guy, or just calculate the short circuit current by shorting out the terminals where the capacitor was?
Because it's pretty simple mesh analysis.
That's fair. So let's approach it from the short circuit current methodology. Okay. So to be clear here, because I see a few confused faces, perfectly reasonable, I am saying that VTH divided by I Norton is R Thevenin. By definition, that's true. The last circuit we analyzed, which is this guy at t is equal to infinity, is the exact circuit we would be analyzing to figure out the Thevenin voltage, right? Because the capacitor was behaving as if it were an open circuit. So the capacitor voltage would be our open circuit voltage or our Thevenin voltage. Tyler. Fantastic question. VC of 0 minus is not during the transient condition. It's before the transient condition occurred. That is a fantastic question. Okay, because that's a very common mistake that people might make here. Our time constant depends only on how the system is behaving during the transient, not before the transient, not particularly after the transient, only during it. All right, so if we're going to employ our Norton current methodology, we are trying to find this current I Norton, and I believe Ian suggested that we approach this using mesh analysis, which I believe to be the most straightforward way to go about this. So here's current I1, here's I2, here's I3, and we can see, so let's not forget it this time. I have a dependent source. So how do I express that current IA in terms of my mesh current? Just I1. All right, I have a current source. What is my current source relationship going to be? Exactly right. So from this, we could say that twice I1 plus I2 minus I3 is equal to 0. Somebody tell me if I did my algebra wrong. I just substituted in I1 for IA, moved I2 over to the left-hand side, moved I3 over to the left-hand side. All right, what do I need to do next? Kirchhoff's voltage law around either mesh 1 or super mesh 2 and 3, right? Which one do you guys want to do first? All right, mesh 1. Kick it off, somebody. Negative 12 volts, all right. And then I'm going to combine those two 6 kilo ohm resistors in series together to look like 12 kilo ohms. Multiply that guy by I1. What comes next? And that's it. Now we have KVL at super mesh 2, 3. Something else getting going on that? Four kilo ohms times I2 minus I1 All right, somebody else, what's next? All right, 6 kilo ohms times I2. All right, what's next? 3 kilo ohms times I3. And we're equal to 0. All right, so that's equation 1, 2, and 3. So we would solve those guys. What did people get? What about I2? -1/9. And just to ask here, did you pay attention? So should this be amps or milliamps, or did you pay attention to units? Should be milliamps. Okay. And what about I3? 4/3. All right. Okay. So now that we know what those 3 currents are, what is I north? Yeah, so 4/3 of a milliamp. I3. And from this, R Thevenin will be our open circuit voltage from T at T is equal to infinity, which I believe we found to be 12 volts. Oops. Roll correctly. Over 4/3 of a milliamp. So let's see, that'll be 36 over 4. So I think that is going to be 9 kilo ohms. My math is correct. All right. So what is our time constant? It's at 9 kilo ohms times 100 microfarads. Which is 0.9 seconds. And the inverse of tau would be 10/9. Right. Any questions about how we did any of step 4? All right. So what's step 5? Plug this crap into the generic equation and finally be done with this terribly long problem, right? You will not. This is much harder than anything I would ever put on your test. If this is making sense, you're in fantastic shape. Skylar, how can I help you? Seconds. So a time constant is a measure of time. It's how long it takes for the signal to decay. So the unit should be seconds.
We just figured out how long that
So if 1 tau is 0.9 seconds, it would take roughly 4.5 seconds-ish for that capacitor to fully charge or discharge. Because 5 tau is infinity for engineers. So, all right, so. Sorry, Joy. We good? All right. So our generic equation as a reminder is now y as a function of time is equal to y at 0 minus for t less than 0 minus and y at 0 plus minus y at infinity e to the minus t over tau plus y at infinity t greater than or equal to 0 plus. So if I were interested in my capacitor voltage, what should I have? What was the capacitor voltage at t is equal to 0 minus? 16 volts. The capacitor voltage at 0 plus must have continued to be 16 volts. The voltage at t is equal to infinity was 12 volts. So 16 minus 12 is 4. So we e to the negative 10/9 t plus 12 volts for t greater than or equal to 0 plus. Literally just plugging stuff into our equation. What if we were interested in that resistor current, IR? Exactly right. So let's do it. Plug in those numbers. So what was our resistor current IR at t is equal to 0 minus? 2 milliamps. Yeah, go back through your 5 pages of working this problem. 2 milliamps for t less than 0 minus. Okay. What was it at y is equal to 0 plus? I think it changed. $1.722. All right, so 1.722, let's write that down here. And what was it at t is equal to infinity?
1.5.
Positive 1.5, all right. All right, so 1.722 minus 1.5. 0.222. All right. 0.222 e to the minus 10/9 t plus 1.5 milliamps for t greater than or equal to 0 plus. I would love to show you guys how to simulate circuits so that we could prove that we're absolutely correct. The only problem with that is you would never have to do math on any of your web work problems again, so I'm not going to do it. But you will, for those of you who take circuits 2 with me, we'll find out that you can easily simulate these circuits and verify these analytical solutions, and they match what happens exactly. It's pretty wonderful. All right, it is 4:10. It's Friday. See you later.